third talk today by André Goddu. André Goddu is a professor at the Department of Physics, is emeritus at the Department of Physics at Stonehill College near Boston. And he has taught history of late medieval and early modern astronomy. He has a book on William of Ockham and one on Nicholas Copernicus, and has published many articles, but he has also dealt with Ludwig Birkenmeyer's studies of Copernicus. I did not know, I have to confess, who was Birkenmeyer, but now I took a look into it and it looks very, very interesting. A Polish historian of science, physicist, and astronomer. And I wonder, he's not mentioned in the title of André's talk for today, but I would not be surprised that he will somehow surface over there. The title of his talk today is Copernican Mereology and the Linear Ratios of the Planetary Spheres. Please, André, go on.
Thank you. Thank you very much for the introduction. I am not going to refer specifically to Birkenmeyer, but I'm glad you mentioned him because my translation of his book is going to appear sometime within the next few months. That is nearly complete, and I hope it will be out no later than May. And you're right to think that much of what I have to say about Copernicus is very much dependent on what I found in Birkenmeyer. And it's unfortunate that he was not translated, much earlier, but I think there's still much value in his work. So with that, I suppose I should try to share my screen and hope that I get it right this time. Uh-oh. Oh, there it is. All right. All right. Is that correct? Can you see that?
Yep.
If you can put it in presentation mode, I think it will be better. But it may work as well over there. If you have only text, it will be the same.
Okay, I'm sorry. I didn't quite hear that.
Okay, go on.
All right. All right. Well, so on to the, let me do it this way. Okay, so you're all familiar with these terms, of course, but let me nonetheless explain what is going on here. So there are two parts to my paper. One has to do with Copernicus's use of whole-part relationships and what he derives from that and how he uses it to criticize the Ptolemaic system and geocentrism in general. And then the second part is the application of these ideas that led him to his two most important results, the determination of the proper order of the planets, and then the estimates of the relative linear distances between the spheres. So I'm going to try to connect those two in this talk. So by Copernican Mereology, I mean Copernicus's belief that the universe is whole, finite, complete, and perfect. I'll come back to the finite part later. In his critique of Aristotelian and geocentric and Ptolemaic geocentrism, Copernicus applied the dialectical topics from an integral whole and from an integral part to evaluate geocentrism. Because judgments about the structure of the universe depended on fallacious inferences from our experience of the part to the structure of the whole, he concluded that geocentrism was the source of the main problems with ancient astronomy. He expressed this most clearly in the dedication letter to Pope Paul III, which is what you see before you now, the first part of it. So let me just read this with you. Ptolemaic astronomers were unable to discover or deduce from eccentrics the principal consideration, namely the form of the whole of the world and the certain commensurability of its parts. Instead, they acted like someone who took hands, feet, a head, and other bodily parts from diverse individuals, each well depicted, but without correspondence to a single body, because the parts did not fit together at all, with the result that from them they composed a monster and not a human being. So that's a familiar criticism that I'm sure you all know. Therefore, in the process of demonstration, which they call method, we discovered that they have either omitted something necessary or admitted something foreign and not at all pertinent. This would not have happened at all had they followed certain principles. For if the hypotheses assumed by them were not fallacious, everything that follows from those hypotheses would have been verified without doubt. There have not been a lot of commentaries on that particular statement in the editions of Copernicus's work. So I'm going to begin then to focus on the idea of the incoherence of the Ptolemaic system. So first, each planetary sphere has a different eccentric point, meaning that Ptolemy's models are a patchwork of individual models that do not fit together into a unified whole. Second consequence is that Ptolemy resorted to a model to save uniform planetary motions by having them move around a point that was not the center of motion, so it's the equant, a contradiction of the axiom of uniform circular motions. A further consequence of Ptolemy's system is that the ordering of the planetary spheres was entirely arbitrary. The superior planets were ordered according to their sidereal periods. So Mars, Jupiter, and Saturn are ordered according to their sidereal periods, but the paths of the inferior planets, Mercury and Venus, were measured by their zodiacal periods, that is, their annual motion with the sun around Earth. It was impossible to settle the question of the ordering of the spheres because there was no consistent mathematical principle governing their motions around Earth. In other words, Mercury and Venus were located differently in varying geocentric systems. So Plato places them above the sun or beyond the sun, Martianus Capella around the sun, and Ptolemy below the sun. In short, geocentrism could not settle the question of how the planetary spheres were ordered, and its models were, in addition, incoherent. So the part about not being able to settle questions about the order of the spheres was to Copernicus a scandal, and perhaps the most important reason why he thought the problem lay with geocentrism. Copernicus's insistence on the connection between hypotheses and consequence is based on the structure and coherence of the whole, and on the commensurability of the parts. So Copernicus's view seems very close to the notion that the validity of hypothetical arguments depends on pertinent or relevant relations between hypotheses and consequence that are recognized by topical maxims such as integral, whole, and part. That topic served both as the justification for Copernicus's critique of the Ptolemaic system and for his vision of the universe, according to which the existence of the whole depends on the existence of the parts, but it is the whole that determines where and how the parts fit in the whole. Our modern rejection of an intuition about the entire universe should not obscure the extent to which thinkers in the 16th century routinely regarded the cosmos as finite, complete, and unified. Now, of course, there are exceptions, especially to the part about infinity, but I believe I'm correct in thinking that most believed that the universe was finite at that time. In the much earlier Commentariolus, circa 1510, in the first section and paragraph after the postulates, Copernicus declares that the immovable sphere of the fixed stars contains and gives position to all things. Later, in Revolutions 1, chapter 8, in his discussion of mobility and immobility, excuse me, he declares that it would seem quite absurd to attribute motion to that which contains and locates rather than to that which is contained and located, that is, Earth. Copernicus's hypothesis, however, was not just the resurrection of a cosmographical theory, but the ground of his reformation of Ptolemaic geocentric astronomy. As he criticized the incoherence of geocentric astronomy, he hoped in his earliest version to replace the multiple Ptolemaic eccentric points with a single common eccentric for all planetary spheres, a homo-eccentric system. Later observations forced him to restore multiple eccentrics, but in both his earlier and later versions, what remained were two results that were the same in both versions: the ordering of the planetary spheres according to their sidereal periods, and the subsequent estimate of the relative linear distances of the spheres from the sun. With Earth in the third sphere from the sun, Copernicus saw that the interior planets, Venus and Mercury, are between Earth and sun in that order because of their differing maximum elongations from the sun. That required Copernicus to replace their synodic periods with their sidereal periods, and that required a calculation. So first, again, you'll see that there's a similarity with respect to the synodic periods of the superior planets, motions related to the sun, Mars nearly 2 years, Jupiter nearly 12, and Saturn nearly 30, the average time between successive oppositions with the sun. But for Mercury and Venus, the average time between two conjunctions with the sun. So you see, if you just take the synodic periods, you can't really see any kind of order. So what Copernicus needed to do then was to use the synodic periods for Mercury and Venus to calculate the sidereal periods. Now, this was a reconstruction by Bernard Goldstein. So Copernicus's calculation involved this. Let me just take you through this quickly, and then we can turn to Mercury briefly, just to show you how it's likely, we don't have Copernicus's own calculations about this, but how likely it is that this is how he arrived at the sidereal periods. So according to Almagest 9.3, Venus as seen from Earth makes 5 returns in about 8 years. So you multiply 8 by the Julian year, 365.25 days, divided by the 5 returns. And that approximately amounts to 584 days. Hence, the synodic period of Venus is about 584 days. In 584 days, the Earth, Sun, and Ptolemy moves 584 days times 0.9985 degrees per day. So it's a little less than a degree per day. So it equals 575.5 degrees. Venus is closer to the sun than Earth is, and Venus moves more quickly. So it makes a complete revolution plus 575.5 degrees. So if we take that 575.5 degrees plus 360 divided by 584 days, we will get 1.6 degrees per day times 360 degrees divided by 1.6 degrees per day is equal to 225 days. So the sidereal period for Venus then is 225 days, or about 7.5 months. Copernicus evidently made a mistake and set it at 9 months, but computational errors are not atypical in his texts. All right, now for Mercury, so I'm going to simplify this one and get it down to the synodic period to begin with that. The synodic period is 116 days. In that time, the Earth's sun moves 116 days, again, a little less than 1 degree a day, 114.33 degrees. and making the same calculation again, we end up with 88 days. So Mercury makes a little under 3 returns in a year. And the result of that, as I indicated, is 88 days. And here's the average time between alignments with the same star, sidereal periods. So you can see they're ordered from Mercury, Venus, Mars, Jupiter, and Saturn. Thus, the planets are ordered according to their sidereal periods. In Commentariolis, Copernicus has 88 days, but only 80 days in revolutions 110. All Copernicus needed to confirm was that the distances increase with the increase of the periods. So even his errors and approximations sufficed. That is to say, all the planets were placed in order from the sun uniquely according to their sidereal periods. With the proper ordering settled, Copernicus could then estimate their relative linear distances. This task did require the application of trigonometry. Before I explain those computations, however, some background on Copernicus's sources and his knowledge of trigonometry. Ptolemy was indispensable to Copernicus, but a Latin edition of Gerard of Cremona's translation was not available until 1515. So Copernicus relied earlier on the Feuerbach Regiomontanus Epitome, published first in 1496, on an edition of the Alphonsine tables from 1492, and on Regiomontanus's Tabulae Directionum et Profectionum, 1490, which also contains Regiomontanus's table of signs. A second possible source for Copernicus was Jaber ibn Afla, whose works were known in Krakow in the 15th century, often cited, often used, and it's very likely that Copernicus first learned trigonometry from Albert of Bujevo, who relied on Jaber ibn Afla. A third and certain source was Giovanni Bianchini, who was Copernicus's source for his latitude theory, and from whom Copernicus very likely adopted the decimal version of sign values. Copernicus's own trigonometry has been the subject of some controversy. Some of it stems from computational errors and some from typographical errors in the 1543 edition. Copernicus followed Ptolemy, probably after the version in the Epitome, that he made some adaptations. Already in the Uppsala notebook, so this is a notebook that is contained in one of the books now at Uppsala, in which he made, he constructed a lot of his own tables and made his own calculations. So already in the Uppsala notebook, and in Commentariolis, Copernicus used the sign values for the radii of epicycles available from Ptolemy and the Alphonsine tables. Rather than work out his own trigonometry at that point, however, the task he reserved for the promised longer work, he found in the tables the numbers he needed to transform them into the relative linear distances of the planets of his theory, aided by Regiomontanus's Epitome, Book 12, Theorems 1 and 2. Now, in Regiomontanus's section of the Epitome, Book 12, Proposition 1 or Theorem 1, this is an image from a version of the book that I found in Vienna, and that an annotator added sketches to. This particular theorem in Book 12 is a proposition in which Ptolemy shows how you can take an epicycle different model. So here's the deferent circle, the epicycle here, And you can replace it with an eccentric. And this, he says, can be done for the superior planets, Mars, Jupiter, and Saturn. Now, what's not clear from this is how you can account for retrograde motion using an eccentric circle. But nonetheless, Ptolemy presented this as an alternative way of trying to account for the motions of the superior planets. Now, the part here that's of interest is that the radius of the epicycle is equal to the length of this eccentricity from the center to this point here. And the sine value for the radius of the epicycle was determined by Regiomontanus. And this is what Copernicus relied upon to construct his own account then of the motions of and the relationship of the various planetary spheres. Now, this is an image. I will show you details in just a moment, but this is from the Uppsala notebook, folio 284V. You can see the 284V here. And let me move to the next so you can see the top more clearly. So this is the top part of it. And here he says eccentricitas Marti, and then gives you the number. That is the sine value from Regiomontanus's, not Regiomontanus, but rather from the Alpine sine tables. So it's 6583. Then he calculates the epicycle. So there's a bi-epicyclic construction in the Commentariolus. And then comes Jupiter, Saturn, Venus is missing, and then Mercury. Now you'll notice for Mercury, we have a number that's hard to read because he corrected it. It's 2256. But over in the margin, he wrote 376. I'll explain that in just a moment. So this is the upper part of folio 284V, the planetary eccentricities, which when multiplied by 6, give you the values that are found in Regiomontanus's table of sines. And those correspond to the angles of anomaly for each of those planets. All right, so Mars 6583, the angle of anomaly is 41 degrees 10 minutes, and these are the sine values in Regiomontanus in a sexagesimal form. All right, the lower part of folio 284V is about the proportion or the ratios of the orbs relative to an eccentricity of 25 parts. So this is where Copernicus calculates how the planets are ordered. So he begins again with Mars, Jupiter, and Saturn. Here he does include Venus, and here is Mercury, using the astronomical symbol for Mercury. All right, so here's the lower part. So we take Mars, the sine value was 6583. If you take the radius as at 10,000, so you see he's using the decimal version here, divided by the eccentricity is equal to 1.52. And here are the rest for Jupiter and Saturn. For Venus and Mercury, he has to reverse them because they're interior planets. And when he scales them to 25 parts, here are the results. So Mars is set at 38 to 25. So 25 is the astronomical unit that he uses for the distance between the sun and the earth. So 38 to 25 produces a ratio of 1.52. And here you can see the remaining distances. So if we put them in order, we would start with Mercury at 9.24. He made a mistake in that calculation. Then comes Venus, then Mars, then Jupiter, then Saturn. All right, so it corresponds to the order that he had already determined previously. All right, so let me go through that a little bit, and then I'll come back to my final reflections and random thoughts. Put as simply as possible, the numbers at the top of folio 284V of the Uppsala notebook are geocentric. To explain the relationship between the numbers in the notebook, the Alphonsine tables, and Regiomontanus's table of signs, I've suggested the following interpretation. Copernicus multiplied the eccentricities in the top part of the note on folio by 6, but did not explain why. Throughout the 15th and 16th centuries, authors used varying numbers for the radii, some expressing them in terms of 6,000 or 60,000 using the sexagesimal system, others using 1,000, 10,000, 100,000, or even 10 million. Copernicus's source for the sizes of the eccentricities was probably the Alphonsine tables, which set the radius of a circle at 10,000, but he may also have been following Bianchini here. The table of signs in Regiomontanus's Tabulae Directionum, however, set the radii at 60,000. From the angle corresponding to the minimum equations of anomaly when the epicycle is at mean distance from Earth in the table of signs, Copernicus had to multiply the maximum sign values he cited in the notebook by 6, making the radii 60,000 and correspondingly the eccentricities 6 times larger. For all the planets, the results then are as you see before you. So the angle in the above table refers to the angle from Earth to the epicycle center to the planet on the epicycle, so the angle of anomaly, when the epicycle is at mean distance from Earth. The radii of the planetary orbs, assuming that the heliocentric theory has already been formulated and the order of the orbs determined, is as follows. So that's the the slide that I showed you earlier. Copernicus rounded off the solar eccentricity 26 and 28/60ths from the Alphonsine tables to 25 parts. The switch in the Ptolemaic Alphonsine numerators and denominators for Venus and Mercury is due to their order inside Earth's annual path. The value for Venus has been corrected slightly, and in the case of Mercury, Copernicus made a calculatory mistake. It should be 9.4, but instead he calculated 9.24, one of many that entered into his texts and notes. To make the point as clear as possible, notice that the numbers for estimating the relative linear distances are potentially already in Ptolemy. The numbers at the top are geocentric, but they cannot be transformed into the numbers below without determining the order of the planets. Copernicus had already formulated his theory and determined the proper order of the planets so that what was potential in Ptolemy became actual in Copernicus. And so now, finally, my final reflections and random thoughts to conclude this presentation. Now, in the question of the, excuse me. On the question of the infinity of the universe, there has been some confusion. As far as the stellar sphere is concerned, there is no question that Copernicus believed it to be finite and have a finite distance from the sun. The inability to confirm stellar parallax through naked eye observation implied the possibility of an infinite universe, but for Copernicus, it implied an indefinite and unknown distance, not an infinite one. Now, of course, that will change over the course of the 16th and 17th centuries. Second, while Copernicus displayed no explicit interest in questions about the ontology of numbers, mathematical speculation about infinity and the like, he belonged to a tradition of thinkers who viewed the universe as intrinsically mathematical. And I can appeal also to the earlier talks that we heard today, and also earlier talks that about these views that go back to Plato and also Aristotle to some extent, but especially Plato and the Pythagoreans, about the intrinsically mathematical nature of the universe. By comparison with the deep discussions conducted by philosophers on the nature of numbers, of geometrical elements such as points, lines, and figures, and of infinity itself, Copernicus seems rather naive in his adoption of the idea of the intrinsically mathematical nature of the universe. He was in this regard a follower of Plato and Ptolemy, and no doubt influenced by what he understood of Pythagoreanism. He was obsessed with questions concerning the coherence and unity of the cosmos. As a follower also of Aristotle in some respects, it seemed self-evident to him that the cosmos was a composite whole, created according to certain mathematical principles. He believed that those mathematical principles are discoverable, and that the cosmos itself provides the evidence needed for us to discover them. His great contributions were to discover one of those mathematical principles, the unique ordering of the planetary spheres according to their sidereal periods, and to compute from Regiomontanus's trigonometric tables the ratios of the linear distance of the planetary spheres from the sun. Third, I have focused on application of mathematics. As I reflected on some of the issues raised in these sessions, and in particular at the last session concerning measurement, graphical representations, the reliance on various versions of Euclid, the modifications introduced into the theory of proportions and so forth, I could hardly fail to recognize, as Daniel Domitian noted in his presentation, the extent to which astronomy, with its centuries of observational data, provided the basic raw material for problems and their solutions. Astronomers' efforts were not conducted, however, in the absence of philosophical assumptions or theories about the nature and structure of the universe, or about the nature and motions of celestial bodies. From the start, the use of geometry and what we later call trigonometry were indispensable for the description of the heavens and the prediction of future positions. All, however, subordinated to their philosophical commitments. I wonder whether the distinction that we make between pure and applied mathematics obscures the extent to which the methods of ancient and medieval mathematicians involved solving problems against the background of their philosophical versions, however much their philosophical visions, however much they may have aimed at formulating the theoretical foundations and deriving theorems from those foundations. Some historians have distinguished between scientific and sub-scientific mathematics, which is perhaps an improvement to the extent that mathematicians in both engaged in problem solving, but problems more theoretical or abstract as contrasted with those of a more practical and concrete nature. In the case of astronomy, the theory was subordinated to natural philosophy, but Copernicus challenged the subordination to geocentric natural philosophy. And while the result was perhaps inadvertent, he provoked problems in natural philosophy itself, especially about the motions of all bodies, celestial and terrestrial. The failure of philosophers and mathematicians to mathematize what they took to be Aristotelian rules of motion, impetus theory, and so on, along with the developing awareness that they lacked the sort of data that astronomers in the late 16th century devoted decades to making ever more precise rendered the subordination of astronomy to natural philosophy, or restored the subordination of astronomy to natural philosophy, but one based on different assumptions. And with that, thank you. I'm done.
Thank you very much. Again, a great talk. We had a very interesting series with differences and touching upon different fields, but at the same time, I think there is a very interesting connection among all of them. So.